And hearty good morning, everybody, and welcome back to Abstract Algebra. Gosh, more energy in this class than in my 3 other classes combined. Plan for today is we're going to continue talking a little bit about cosets, and then get to a proof of Lagranges theorem, our second sort of big name theorem of the semester. Got our usual office hours this afternoon from 2 to 3. As a reminder, you have an exam that is due tonight. You have till the end of the day to submit it. It's due at 11:59 p.m. Other than that, your homework is to have a good break and make sure you are COVID cautious over the break, especially if you are traveling anywhere. We do not need another outbreak of COVID where half the campus goes into quarantine again. We can help it. And that's easy to happen if y'all are not being careful as you're traveling and such. So please do that. Anybody have any questions or comments before we get started for today? Okay. Several people were asked one day, what is 2 times 2? The engineer whips out his graphing calculator, presses a bunch of buttons, and finally says 2 times 2 is 3.99 plus or minus 0.01. The physicist consults her technical references, sets up the problem on her computer, and says 2 times 2 is somewhere between 3.98 and 4.02. The mathematician thinks for a minute and says, I don't know what 2 times 2 is, but I do have a proof that an answer exists. The philosopher smiles and asks, what do you mean by 2 times 2? The sociologist says, I don't know what 2 times 2 is, but it sure was nice talking about it. The biologist says 2 times 2 is a polygamous mating system. And finally, the med student says 2 times 2 is 4. The others all look at her amazed. Finally, the mathematician asks how she knew that. She says, oh, I memorized it. Okay, did I hit record? I did hit record. I always get nervous a couple minutes in. I have to check. So, in class on Monday, we were talking about cosets, where if G is a group, H is a subgroup of G, and A is just some arbitrary element in the group. We can define a left coset of H to just be the set where we take everything in H and multiply it on the left by A, see what we get. We also talked about how you can form right cosets by taking everything in H and multiplying it on the right by your element A. The difference between and ha. As a quick example, just so we remember, if our group is D3, the dihedral group on a triangle, H is the set containing E, the identity in RS, which is a subgroup, and our element A that we're going to be multiplying by is R. Then we would get a left coset by multiplying by R, where we would just take the elements E and RS and multiply both of them on the left by R, and that would give us R and R squared S. Whereas if we multiply on the right by R, that gave us the identity times R, RS times R. Remember, when I say times, I really mean function composition. And that simplified out to R and S. And we made we noticed a number of things last class, namely that left and right cosets don't have to be equal to each other if we're multiplying on the left and the right by the same element. They might be equal, but they don't have to be. We said that it's possible for 2 left cosets to be the same set, even if we're multiplying on the left by different things each time. What else did we say? All cosets have the same size as the original subgroup H, and etc., etc. And so what we were doing towards the end of class last time is we were looking at this lemma on the second page of the packet, where we had sort of 9 different properties that cosets have to satisfy. And we kind of talked intuitively about several of them. But I thought we could start out today's class by actually going through and proving, in my mind, what the most interesting one of them is, which is the 5th one. And so it's going to be a proof, it's going to be kind of number 5 in our lemma, which says if H is a subgroup of G and A and B are elements in G, then A and B will generate the same coset if and only if the two cosets are not disjoint, if they have non-empty intersection. So in other words, AH is equal to BH if and only if these two cosets have at least one element in common. So in other words, if you have two left cosets, if the two cosets are not exactly the same, then they can't have any elements in common. Whereas if your two cosets, left cosets, AH and BH, have at least a single element in common, then they're going to have all elements in common and be the exact same set. If you notice, we have to be comparing two left cosets or two right cosets for this to work. It's possible to compare a left coset and a right coset that have some elements but not all elements in common, like what we see here. This left and right coset both have R, but they're not exactly the same. So it's okay for a left coset and a right coset to have only some elements in common. But if you're comparing two left cosets, or if you're comparing two right cosets, the only way for them to have any elements in common at all is if they have the exact same set of elements. So let's prove this. This is an if and only if statement. So we have two things to prove. We have to prove that the left thing implies the right. If the two cosets are the same, then they have non-trivial intersection. And we also have to prove from right to left that if the intersection isn't the empty set, then the two cosets are equal. Which direction do you think should be really quick? One of these directions is basically like a one-line argument. From left to right or right to left, that's going to be the quick one. That one?
Right to left.
Right to left. So your claim, if you know that the two cosets have at least one element in common, it's very easy to say that they have to be the exact same.
I don't know. Maybe.
You want to phone a friend?
I don't know. Which one?
I would say left to right because if they're equal, then of course they have something in common because they have everything in common.
Yeah, I think from left to right is going to be the quick argument here, and basically saying if the two cosets are equal and have every element in common, then they must have at least one element in common. So proof for left to right is if AH is equal to BH, then AH and BH must clearly have at least one element in common. And so their intersection, the set of elements that lie in both of the two cosets, can't be the empty set. The intersection is not the empty set saying there is at least one element that exists in the intersection of the two, if they're the same. If they're the same, then they have to have every element in common, therefore they have at least one element in common. Okay, fine, 2 lines. The other direction is the more interesting one and the much harder one to prove, which is going to be if they have at least one element in common, then they have to have everything in common. Right to left. So let's suppose that the intersection of these two cosets is non-empty. Meaning, suppose that AH and BH have at least one element in common. Well, then that means there has to be an element that they both share. Let's I'm going to call it x. So you could say then, for some element x in the group, x is going to be an element of AH, and x is going to be an element in the left coset BH. If they have non-empty intersection, if there's something in the intersection, then we can say, well, we have some element x that has to lie in both of these two cosets. Since x is going to be in the left coset AH, what does that tell us about how we can write x? From the fact that x is in this left coset A, little a, h. How can we use that to write down something for what x must be equal to? Wayne?
Little a times some little h in h.
Yeah, then x has to be equal to little a h for some little h in the subgroup h. And similarly, if x is in the coset BH, little b times big H, what does that tell us about how we can write down a formula for little x? Megan?
B little a, negative.
Like that? Make sense? Wayne?
Should we make those little h1 and little h2? Or?
Yeah. You gotta be sneaky here. Just because x is in the coset AH and x is in the coset BH, we don't necessarily know that these two little h's have to be the same. X could be equal to little a times one element in H, and also be equal to little b times a different element, potentially, in the subgroup H. So we don't know these h's are the same, so I'm going to call this one a, I'm going to call this one little h, and this one we'll just call little h prime. So x is equal to AH, and x is equal to BH prime. By the way, if x is equal to little a times little h, it's going to be useful to have a formula for a here in a second. A is going to have to be equal to x times h inverse, which this just follows from multiplying both sides of this equation on the right by an h inverse. And now, we're going to say, now I think we're ready to prove that the two cosets have to be exactly the same. In order to show these two cosets are exactly equal to each other, what we can do is our kind of standard method of showing two sets are equal. We take an arbitrary element in the first and show it has to also lie in the second, and then take an arbitrary element of the second coset and show that it has to lie in the first. Because if every element of the first coset lies in the second, and if every element of the second coset lies in the first, then they have to be exactly the same set of elements. So let's show that everything in the first coset has to be in the second. So I'm going to let G be an arbitrary element in the first coset, AH. So if we have some arbitrary element G in this first coset, little a times H, how can we rewrite G? In order for G to lie in the coset little a times the subgroup H, what does that tell us about the form that G should be able to take? See, I have to get some. See, anyone other than this little group of troublemakers up front?
Me, I haven't even been here.
I know, that's how you've been causing trouble.
Straight materials.
So if little g is in this coset, little a times h, what does that tell us about how we can write little g? Am I?
A H2.
A h hat, I'm going to call it, for some h hat and h. If G is in this coset, we know it has to be A times some element of H, but it doesn't have to be the same as this element in H. It also doesn't have to be the same as our H prime, so we need a third element in H here to talk about a third arbitrary element of our coset. But if you want, you can call them like H1, H2, H3, H not H1, H2. I'm deciding to be a little bit more whimsical and calling them H, H prime, and H hat. Yeah, whimsical. So that just comes from G being in there. And our goal is going to be to show that G has to also be an element of this coset, BH. So check this out. So G has to be equal to AH, a hat. But what do we know about A? We know that A has to be equal to X times H inverse times H hat. But wait, there's more. We also know what X has to be equal to. X has to be equal to B times H prime. Meaning that G has to be of the form B times H prime times H inverse times H hat. What do we know about this product of H-related things? If we take H prime multiplied by H inverse and we multiply again by H hat, what does that product have to be an element of, Megan?
Big H.
It has to be an element in big H. And so G is in fact going to be equal to B times some element in big H. Thus, G is going to be an element in this left coset, little b times big H. So in other words, we've taken an arbitrary element in the left coset little a times big H, and we've shown that that element has to then lie in this coset, left coset little b times big H. What questions y'all have about this? Any questions or comments on this one? So we relied on the fact that we had some elements that lied in both of these two cosets. X is in both little ah and little bh. We relied on the existence of an element in both to somehow show that an element in the left coset little a times big H has to also be in the left coset little b times big H. And then, then we can say thus, little a times big H is a subset of little b times big H, because we've shown that an arbitrary element in this first coset has to also be in the second coset. And then we could do basically the same argument in reverse to show the second is also a subset of the first. So by a similar argument, little b times big H has to be a subset of little a times big H. You basically just do the same argument. You take a little g and little b times big H, and you get a very similar string of equations. And so the two cosets must be equal. And we've done. We've proven the result that the two cosets are exactly the same if and only if they have at least one element in common. If they have at least one element in common, then that's enough for them to have to be the exact same coset. I wrote the lemma in terms of saying things about left cosets, but you could have replaced these left cosets with their corresponding right cosets, and the lemma would still be true. Ha equals hub if and only if ha and hub have a non-trivial intersection. It's basically the same argument. Just swap all your AHs and BH primes with HAs and HB and H prime Bs. But This tells us then, if you have two left cosets, or two right cosets, and if those two left cosets have at least one element in common, then they have to be the exact same collection of elements. All right, it's time for the big theorem number 2. So, I encourage you, I don't know, I'll probably give you at least 1 or 2 of these rest of lemma questions as like a homework set at some point. Well, none of these I think are too bad to prove. You just kind of gotta follow the definitions, use your nose, and rely heavily on the fact that if we have a subgroup, then the identity element has to be an element in it. But what I'm going to do now is I'm going to go to the next page of the packet. We are going to prove Lagrange's theorem. What's that?
Is this like the same Lagrange?
Like the same man.
Is this the same Lagrange, just like Lagrange multipliers?
Yeah.
Sort of Lagrange? No.
Oh.
Multiple Lagranges. There's more Lagranges floating around out there than you might know about. Hey guys, I think someone asked me the same question a year ago and I looked it up and the answer was no.
Oh.
Yeah.
I've always said they're greater than or equal to 1.
They are greater than or equal to 1. In fact, they're greater than or equal to 2. So here's what the theorem says. We're going to let G be and this is Lagrange's theorem. We said let G be a finite group. And H is going to be a subgroup of G. Then, 2 things have to happen. The order of H has to divide the order of G. And 2, the number of distinct left or right cosets of H and G which is going to be called the index of H and G, is going to be given by, you sort of have in, sort of looks like you have these, I don't know what you call these, like matrix brackets or something. G colon H is what you denote with the number of left cosets that H has in G. And that's going to be given by the order of G divided by the order of H, is what this theorem claims. So this is sort of a definition and a theorem all baked into one. So the number of left cosets that H has in G is just going to be the number of elements in G divided by the number of elements in H. So if you recall, if you look at this first part of Lagrange's theorem, we've already proven this for cyclic groups. Part of the fundamental theorem of cyclic groups was that if G is a cyclic group and H is a subgroup of G, then the order of H has to divide the order of G. That same property is still going to hold true, it turns out, in an arbitrary finite group. If it's an infinite group, then it doesn't really make sense to talk about. Infinity divides infinity. But according to this theorem, no matter what group you look at, whether it's cyclic or not, whether it's abelian or not, as long as it's finite, the number of elements in any subgroup has to be a divisor of the order of the entire group. Neato burrito. Let's prove this. So our proof, as you might guess, is going to rely heavily on this idea of cosets. And in fact, it's going to actually use several different pieces of the lemma from the previous page. So I'll try and reference which parts of the lemma we're using when. So to start out, I'm going to let A1H, A2H, all the way up to A sub NH denote all the distinct left cosets of H in G. So in other words, when we say distinct, we're saying all of these are different cosets from each other. None of these are the exact same left coset. And we're also saying this is going to give us a list of all of the left cosets. So that any left coset of H you might find is going to be equal to exactly one of these things in this list. We know there has to be a finite number of left cosets, by the way, because G is a finite group. We're assuming G is a finite group, meaning there's only finitely many ways to take a coset of it. So these are all of our distinct left cosets. First of all, I claim that by the first item in the lemma, we know for any element G and G, G is going to be an element of one of these left cosets. That G is going to be an element of A sub I times H for some I. And that's from part one of the lemma, basically saying that G has to be an element in this coset specifically, the coset that's equal to G times H. Well, we know little g times big H has to be equal to one of these things because we said that this is a collection of all the left cosets. So that's going to tell us that, well, G has to be in a left coset, and if this is all the left cosets, then G has to be in one of these cosets specifically. That's by part one of our lemma. By part 5 of the lemma, what we just proved, we can say that if you take any two of these cosets and you intersect them, you're going to get the empty set. If I is not equal to j. So in other words, according to part 5, we're saying if these are all distinct, meaning none of these are the exact same coset, then if I take any two of these cosets, they're not going to be exactly the same, and therefore, by what we just proved, they can't have any elements in common. Their intersection has to be the empty set, nothing in the intersection. So as long as I and j are not equal, a sub I times h and a sub j times h should have no elements in common between the two. So now we can actually prove Lagrange's theorem, which is surprisingly quick. This is not a long proof once we have cosets involved. Thus, we know the order of G should be equal to the order of the union of all of these cosets. And here, I'm going to write in L1 above the equal sign to say that that's from property 1 of the lemma. Basically, if we're using the fact that every element in G has to be in one of these cosets, that then tells us that the number of elements in G should be equal to the number of elements in all of these cosets combined. Just from the fact that, according to lemma 1, the union of all of these cosets should be the entire group. You take the set of all elements that are in at least one of these cosets, that's the entire group, since every group element is in one of those cosets. But wait, there's more. We can also use the fact that all of these cosets are disjoint. None of these cosets have any elements in common. To say the number of elements in the combined in all of these is just going to be the number of elements in the first coset plus the number of elements in the second coset, all the way up to number of elements in the last coset. And so this relies on the cosets having no elements in common, because what we're really saying is that if the number of elements that are in all of the cosets separately have to just be the number of things in the first plus the number of things in the second plus the number of things in the third all the way up to the number of things in the last, because there's no overlap. if these cosets had some overlap between them, then we couldn't say, oh, the number of elements in all of them has to be the number of elements in the first plus the number of elements in the second, etc. We wouldn't normally be able to say that because what if there's some element in both of the first two cosets? We wouldn't want to count that element more than once. Well, this property 5 here that says these cosets have nothing in common tells us we don't have to worry about counting elements more than once. We can just take the number of elements in the first thing plus number of elements in the second thing, etc. And that'll give us the number of elements in the union of all of them, which is the order of G. Let me stop for a minute here and see if y'all have any questions or if I need to slow down. So, in other words, the order of the group has to be equal to the number of elements in the first coset plus number of elements in the second, etc. But wait, there's more. If we use the seventh part of the lemma, the seventh part of the lemma says that all cosets have the same size, that any two left cosets have to be have the same number of elements. Since H is going to be equal to one of these cosets, the order of A1 times H is going to be equal to the order of H. The order of our second coset, A2H, is going to be the same as the order of H. And what can we say about the order of the last coset, A sub n times H? The order of that should be equal to the order of
H.
Indubitably. Yeah, these cosets all have the same size, which is the same size as H. Well, we have n cosets. All have the same size as H. So we're basically adding together n copies of the order of H. What is this expression going to simplify down to? Peter?
N times the order of H.
Yeah, it's just going to be n times the order of H, because we're just adding the order of H to itself n times. And lo and behold, this then tells us that n has to be equal to the order of G divided by the order of H. And since n has to be a positive integer, because it's the number of left cosets, that then tells us the order of H divides order G. And n, by the way, n we said was the number of left cosets. We said let A1 through ANH be all the left cosets. So this n expression is really going to be equal to the index of H and G. And so there, we just proved both parts of the theorem in one fell swoop. We showed that the number of left cosets of H is going to be equal to the order of G divided by the order of H. Well, that was part 2 of the theorem, and in doing so at the same time, since n has to be a positive integer, we're saying the order of G divided by the order of H comes out to some positive integer, therefore the order of H has to divide the order of the group as a whole. Any questions or comments? Boom. We just showed that the order of any subgroup has to divide the order of the group. Doesn't matter what your group is, as long as it's finite. It could be abelian or non-abelian. It could be cyclic or non-cyclic. It could be a permutation group or a non-permutation group. We're going to have a theorem later on that says every group is a permutation group, but that's yet to come. No matter what your group is, any subgroup has to have order dividing the order of the whole group. What's that, Dr. Bursley? You said every group's a permutation group? You bet I did. We're not ready for that one yet. We need to talk about direct talk first. That's Kaylee's thing. Fun result. So it generalizes what we've already proven about cyclic groups to be proven also about arbitrary groups as well. So if we look at a quick example of this, Let's see. Let's look at, I don't know. Let's look at the symmetric group. And then H is going to be A3, which is going to be made up of just the identity and the 2, 3 cycles again. So I claim, so what's going to be the order of G in this case? How many elements were in S3? What was the formula for the number of elements in the symmetric group Sn? What?
It's 3 factorial.
So the order of the group G is going to be 6. The order of H is 3. Hey, the order of H divides the order of G. How about that? Also, if we look at all the cosets of H, here, this is not happy. There's only going to be 2 distinct cosets. There's going to be the coset of the identity times H, which will be equal to 1, 2, 3 H and 1, 3, 2 H. H is also going to have another coset that's basically made up of, and this is just H. There's a second coset that's made up of taking 1, 2 times H, 1, 3 times H, and 2, 3 times H, any 2 cycle times H. And that will give us the set of just, 1, 2, 1, 3, 2, 3. It's going to give us the set of all the 2 cycles. So with that in mind, what's going to be the index of H in our group? In other words, what's going to be the number of distinct left cosets that H has in our group? Here's one of our cosets. Here's the other coset. How many do we have? Okay.
2.
We have 2. We have this one, and we got that one. Which, lo and behold, we have 2 left cosets. 2 is equal to 6 over 3, which is going to be the order of our group divided by the order of the subgroup. So in other words, what our theorem tells us is that we knew this was going to happen without even having to look at all of the individual cosets. We could have just said, how many cosets does H have in G? Well, if G has order 6, H has order 3, then number of left cosets is just going to be 6 divided by 3 is 2. Which, I keep saying lo and behold, I don't know why I'm saying that a lot today. Which, what do you know, there are 2 cosets. Just H itself and the set of all 2 cycles. So Lagrange's theorem will then just tell us this has to hold true for any finite group, regardless of which one you're looking at. Whether it's a symmetric group, it's the dihedral group, it's going to hold true for any cyclic group, so any Z mod NZ you might care about. It's going to be true for any group of units. What else have we seen finite group-wise? Might be it for what we've seen finite group-wise. But any other finite group will always satisfy these conditions, that the number of left cosets is the order of the group divided by the order of the subgroup. And in doing so, since that's always going to be a positive integer, order of the subgroup has to divide order of the group. Questions, comments, concerns? So if you remember, we said that this holds true for cyclic groups, that if G is a cyclic group, then the order of any subgroup has to divide the order of the whole group. What do you all think about the general case? Would it be true that if G is a group of finite order, does G have to have a subgroup of every order dividing the order of the overall group? So if we flip to the next page of the packet, I ask that as a question. if K divides G, the order of G, for some K greater than 0, must G have a subgroup of order K? You remember, for cyclic groups, we said that the answer to this question is yes, it does. That any cyclic group, that if K divides the order of any cyclic group, then that cyclic group has to have a subgroup of order K. And in fact, it had to be unique as well. That was a big part of what the fundamental theorem of cyclic groups told us about the structure of what do all the subgroups of a cyclic group look like. What do you all think about this one? Where I need Peter here, so he can, Peter's not afraid to take a stand. If I show a thumbs up or thumbs down, who thinks this is true? Who thinks this is false? You had to guess. Thumbs down is false, yes. Seeing a lot of thumbs sideways, thumbs leaning down. Turns out this is a false for general groups. While it is true that if K divides the order of a cyclic group G, then G has to have a subgroup of order K, the same is not necessarily going to hold true if G is a non-cyclic group. Any subgroup of G has to have order dividing the order of G, but that doesn't necessarily mean G has to have a subgroup of every order dividing its order. A lot of orders in the same single sentence. And so, here's an example. Example we're going to look at is going to be, G is actually going to be the alternating group, A4. So in other words, the set of all even permutations in S4. And I claim 6 is going to divide the order of A4, but A4 has no subgroup of order 6. What is the order of the alternating group A4? We said the order of A sub n is always going to be 1/2 the order of the corresponding symmetric group Sn. So it's going to be 1/2 the order of S4. How many elements are in S4? Right?
24.
How did you get 24?
4 factorial.
I was hoping you were going to say I counted them all. Yeah, it's going to be 1/2 times 4 factorial. 4 times 3 times 2 times 1 is 24. And this is going to come out to 12. So my claim is that 6 is going to divide the order of A4, so that A4 has no subgroup of order 6. So, oh gosh, we're not going to have time to do all this. And we're going to leave it at that for now. Have a good break, everybody. I was going to say, this is like a 15-minute thing, not a 5-minute thing. And I don't want to get started with an argument just to have to remind you all what it is after the break. So when we come back from the break, we will prove A4 has no subgroup of order 6, despite the fact that 6 does divide the order of A4. Because I've actually got a pretty slick proof that A4 has no subgroup of order 6. It's a fun proof by contradiction. Hope you all have a good break. Remember, stay safe, wear a mask 6 feet away, etc., etc. Wash your hands. And just because it bears repeating, wash your hands. Have a good break.